So the first thing we're going to do is we're going to graph the three parent functions that we've already done. So we're going to start with f of x equals the sine of x. Okay? That's what we are going to start with. And so when we do this, I've had you draw your little parent function of one cycle. Right? And don't get carried away and like put extra stuff. That's what it should look like for sine. There are 5 anchor points there that need to be graphed. The easiest way to do it, because some of y'all I think are still a little bit confused about this, is you graph this one first. Okay? And there's no transformations on here because we're just doing the parent function. So this is at 0, 0. Then the next thing you should do is the end of the period. The period for sine with no transformations is what? 2 pi. So I'm going to put a point here at 2 pi. And then I'm going to put a point halfway in between, which is also an intercept, which would be at pi. Make sense? And then I can do halfway in between the rest. Halfway in between here is the max. And so your amplitude without transformations is what? 1. So it's here at 1. And then it's down here at -1. And then you repeat, right? So look, you have a point, nothing, and then a point, and then nothing, and a point. So over here, when I'm going this way, there's nothing here, and then I should have a point on this x value, but I have to stay in my pattern here. This was on the axis, so this one's below, and then I have nothing, and then a point on this x value, which will be back on the axis, and then this one should be up here, and this one should be back down here, so that you get your sine that ends up going like this. And you try and make it as curvy as possible, not pointy stuff. And there's arrows on the end. Okay, like when you're sketching your parent function, the fact that you're not putting arrows there is fine. But this keeps going, and you need to make sure you understand that. And this is important because we are going to graph some that don't. Okay, that just stop, and you have to know the difference between the two. Are we all good on sine? Okay, because we're about to do the reciprocals. We got to make sure we got these down. Now let's look at cosine. Okay, so f of x equals cosine of x. Right? And so here, when we draw our little parent function for this, it would look something like this. Right? And again, we have 5 anchor points. For the parent function, this starts at 0, 1. So I start at 0, 1. Then I go to the end of the period, which is 2 pi, and this has the same y value as the first point, whatever it happened to be if there were transformations. In this case, it's 1, so I'm way out here. And then everything else is half, half, half. Halfway in between, I get a minimum. So that's going to be down here at pi, but it's at -1. And then halfway in between these two, there's an intercept, so I'm here on the axis. And halfway in between these two, this is on the axis. And then we repeat, right? So every 2 x spaces, you have a value. So I go 2 spaces, and then I'm on the axis, 2, and then I'm below, 2, and then I'm on, 2, and then I'm above. And it has the exact same look as sine because it's just a translation of sine anyway, but again, there are arrows on the end because it continues. Okay, everybody okay with that? Ask me questions if you got questions. I don't know, because it's kind of easier when it's big up here. All right, so then I've got tangent. So the tangent of x, f of x equals the tangent of x. And so I have my parent function. For tangent, we've been drawing this because it's, even though it's like pieces of it, it's way easier with transformations if you go with starting at 0. Okay. Still 5 pieces to graph. This is 0, 0. I'm here at 0, 0. What is the period for tangent? Pi. So then this is at the end of the period, which is at pi. Got those 2 points that are on the axis there, or on the midline if there's transformations. Halfway in between, you have an asymptote. So here's the asymptote right here. Then halfway in between the intercept and the asymptote, you're going to have another point, which is not the amplitude, but that would be a 1 if there's no transformation. So halfway in between these two, I go up to 1. Halfway in between these two, you go down to -1. Then you repeat. There is something on every single x value. So when I'm here, the next x value, I'm going up to up 1, and then I have an asymptote, and then I should be down at 1, and then I should be on the axis, and you just keep up with the pattern. Okay, and there is tangent. Everybody good with all that? Remember what they look like and how to graph them, yes? Because if you can graph these, you can graph the reciprocals, but because we're basing it off of this. So once you're done with that, then grab the paper that has the big graphs on it, not the one that has the title on it, and because that is going on 108. Okay, let's see. So this is what I want. This is going on page 108, yeah. So we are going to graph the reciprocals. Cosecant is the reciprocal of what? Sine. So this is really 1 over the sine of x. Okay? So my parent function here is going to be f of x equals cosecant of x, because that's how you write cosecant. Okay? In order to make this happen, we are going to very lightly, now I can't do anything lightly, I just have to change my color, but we're going to very lightly sketch in the parent function for sine. And so just like a little dotted line, don't make it super dark, because you want to be able to see it so we can use it, but you don't want it to be like the graph itself. So we're going to have points here, and then in between we're going up to 1 and down to -1. So it should look kind of something like this. Yes, we're going to do the whole thing. So just like lightly sketch it in. And the arrows don't even matter on this. Just know that it does keep going. Because remember, the graph itself is giving you those values. So the sine of 0 is 0. The sine of pi is 0. The sine of 2 pi is 0. So the sine of pi halves is 1, and so forth and so on. Okay? Does that make sense to you? Then we're going to go in. From this, we can graph cosecant. We can totally graph this. So I want you to think about the fact that it's just the reciprocal of sine. So if its sine of 0 is 0, what is the reciprocal of 0? Undefined. 1 divided by 0, and that is undefined. So how do you graph undefined? It's an asymptote, right? It's an asymptote. So the reciprocal of 0 is undefined, so that means for cosecant, you actually have an asymptote here. This is also 0, so you're also going to have an asymptote here and here. Everywhere where sine is 0, cosecant has an asymptote because it's undefined. Okay? Does that make sense? Now, let's go back. Let's go to pi halves. What's the sine of pi halves? Just look at the sine of pi halves is 1, right? What's the reciprocal of 1? It's 1. 1 over 1 is 1 over 1, right? The reciprocal of 1 is 1. This is not a trick question. Which means that The sine of pi halves is 1, and the cosecant of pi halves is 1. So this point here, your max and your mins, those are actually points that exist on cosecant as well. Okay? Now what's happening here, these are not inverses, they are reciprocals. So this function is basically getting turned inside out. I'm going to do one more another set of points, which these are the bare minimum of what you're going to have to graph, what you're going to have to plot before you can sketch in your graph, but I want to show you where the other stuff comes from. What is the sine of pi fourths? Square root of 2 over 2. Is it square root of 2 over 2? And you're right, it is. That's not what I meant to ask you. I'm so sorry. What is the sine of pi sixths? That's what I meant to ask you. 1/2, because it was the easier one to do. I was thinking about the wrong thing. So the sine of pi 6. So pi 6 on the x-axis is a little bit before 1, okay? But so when I'm here, I'm at 1/2, right? So the sine of pi 6 is 1/2. What is the reciprocal of 1/2? 2. So for cosecant, you're actually, when you're at pi 6, you're actually up here at 2. Okay? Then when you are at 5 pi sixths, it's also 1/2, right? So 5 pi sixths, somewhere right about here, you'd be at 1/2, but that now becomes 2. Now these 2 points we just plotted, you're not going to have to find them in all the graphs. I just want you to see how this gets turned inside out. Like we can plot a whole bunch more. We're not going to. But what ends up happening now, just between those first 2 asymptotes, do you know enough about graphing an asymptote that you could sketch that part in? It's going to look kind of like a parabola, right? So it's going to look like this. Okay? Does that make sense? So now here, when this one is up here, the same thing is going to happen. And then down here, these happen. Like so. Oh, I missed that one. Okay? Easy enough? Now remember, I'm not going to make you find these points. You're going to have to find the asymptotes and what amounts to 1 on here, which might not be 1 if there's an amplitude change or something. And that's all you got to do. The parent function of sine is going to help you the most. Now let's fill in the stuff down here that goes with it. What's the domain of this function? There's a whole lot of stuff that belongs in it, and there's a whole lot of stuff that doesn't, right? So let's start with that. Okay, so we can start with, it's all real numbers, but x can't be certain things, right? So x cannot be, what's the first thing x can't be? 0, and then pi, and then 2 pi. So it's every pi, right? So n times pi, and remember we had that weird thing where n is an element of the integers? And I promised you, and I told you, and this holds true here. We're writing it here. I want you to think about it and understand it. I didn't ask you what the domains were on all the other ones you were graphing, right? You didn't have to worry about recreating this. Just have a concept of it. What is your range? Negative infinity to what? To negative 1. So we go from negative infinity to negative 1. I can't include negative infinity, but I do include negative 1. And then there's a whole bunch of places I don't have anything, right? Then where do I start over? 1, and then I go to infinity. What goes in between these two? A union. Very good. X-intercepts. None. Yeah, that's kind of what I figured you meant, but I was like waiting for a second. Okay, so none. All right. Y-intercepts? None, because there's an asymptote there too, right? None. All right, asymptotes. Oh boy, do we, right? But remember, these are very much tied together. Why can't x be these things? Because there's asymptotes. So guess what your asymptotes are? X equals n times pi, where n is an element of the integers. The definition of amplitude is half the distance between the maximum and the minimum point. Do we have maximums and minimums? No, we don't. If I don't have them, I can't find the distance, and I can't, so this is undefined. It's still going to have an important, like A is still going to play a part in this, but it's not an amplitude. The period, how far does it go before it repeats? It's actually 2 pi, because this is not the same as this. right? You see how you have to have both of them? So it's the same as what sine was, which is 2 pi. Okay. So your transformations, f of x is equal to a times the cosecant of b times x minus c plus d. And this is with everything all in there. We are only going to do the a and b part of this, okay? So remember that the amplitude is undefined, so we're writing that small, because we still do have an a, right? Then that is your vertical stretch or compression, and that's the absolute value of a. So it still plays a part, just like it did for all the other transformations. It's just not called amplitude, just like with tangent, we didn't call it amplitude. The period is 2 pi divided by the absolute value of b, so you treat it exactly the same way you did for sine and cosine. This is still c, and this is still d, something you should know even if we're not going to graph any of them, okay? All right, we good? All right, so let's look at secant. What is secant the reciprocal of? Cosine. So this is 1 over cosine of x. So f of x is equal to the secant of x. We are going to lightly sketch in the parent function for cosine. Okay, so we're going to get our kind of our anchor points in here so that I don't mess anything up as I sketch it in. Just make it light so it's not the main part of your graph. Because you're not going to sketch it in every time you do it. I'm going to show you a different way to use it, but I want you to see where it's coming from here. Okay, so just like with sine, everywhere there is a 0, what do we have now? An asymptote. Everywhere the cosine value is 0, you now have an asymptote. Then, everywhere the cosine value is 1, what's the secant value? 1, because the reciprocal of 1 is 1. So after you get the asymptotes in there, you can go find all the 1s. And then that's all you have to find, and you should be able to sketch it in. Right? Looks like this. It's the same as the cosecant graph. It's just translated, right? Okay, easy enough? Same thing, because it's just translate, just because all cosine is sine translated over, so we're good. So then once again, your domain, it's all real numbers, except that x cannot equal some things. What's the first thing that x can't be? Pi halves, right? And then every pi after that. So this one is that it can't be pi halves plus n times pi, because you have to account for that shift over, where n is an element of the integers. Your range, it's the same as it was for cosecant, negative infinity to negative 1, and then 1 to infinity. Everybody understands why it's that? Ask me questions if you don't. Do we have x-intercepts? Nope. Do we have any y-intercepts? Yes, what is it? 0, 1. Good, it has to be an ordered pair. Do we have any asymptotes? Yep, and it matches the domain, right? X equals pi halves plus n times pi, where n is an element of the integers. Amplitude, still undefined. What's the period? 2 pi, just like it was for sine, cosine. Okay. Transformations. F of x is equal to a times the secant of b times x minus c plus d. But again, we're only looking at the a and the b. Amplitude is undefined still, but we could still have a vertical stretch or compression, which is the absolute value of a. The period works the same way as it did for the reciprocal, which is 2 pi over the absolute value of b. This is c and this is d, just like it always is. Ask me questions. Anybody got questions? Because I'm not talking and goofing around. All right, let's look at cotangent. Cotangent is the reciprocal of what? Tangent. So this is 1 over tangent of x. So this is going to be f of x equals the cotangent of x. What? Such language. So we pretty much drew in like the whole thing for the parent functions on the other. Not going to do the whole thing on this one because I think it would just be too much on your graph. But we are going to just sketch in the little part that we normally sketch. So for tangent, I normally have you draw this, right? So that's just the part that we're going to sketch on there lightly. It's like in the background so we can come up with it. So I know that I start at 0 and I go to pi. The asymptote is right here. Very lightly. I don't even know that. I'm not even going to draw in that asymptote. I don't want that to confuse you. Just know that it's there. And then halfway in between these two, I'd be at 1. So it would look something like this. And then here at -1, and it would look something like this. Okay? Because I don't want the asymptote that's there to confuse what's going on. Well, actually, I will draw mine in. I'm worried about yours because I can make my colors different. So I'm going to draw mine in. You may want to leave yours off there, and that's fine. Okay. So let's think about this. These are the 5 anchor points that I needed for tangent. So cotangent's the reciprocal. So where I have zeros, what am I going to have now? Asymptote. So I'm going to have an asymptote here and here. So where I have an asymptote, now the reciprocal of undefined is not anything, but the reason that there's an asymptote there is because you were dividing by 0. So if I take the reciprocal of that, I actually get 0. I mean, it's technically the reciprocal of undefined is not 0, but for our purposes here, that's where the 0 ends up, okay? So then when the value of tangent is 1, what's the reciprocal of 1? 1. So I still have a point here and here. Those are the same points, just like they were. What ends up happening for tangent is those asymptotes move, and then your curve goes the other way. Does that make sense? So now this looks like this. So it looks a whole lot like tangent, almost like tangent was reflected and then shifted over. But I mean, it's not exactly what was happening, but so then we just repeat that. So every pi, you have an asymptote still. You have zeros in between, and then you have not an amplitude, but you do have that one value that's important. And it looks like this. So do you see how I get this from what I had? That's because that's going to be kind of important for you when you're graphing it. What? Oh, okay, I see what you're saying. It's your, I can't ever think of the word. It's your scale. So, The scale is 1/2 instead of 1 is basically what he's saying. All right, so your domain. Well, we have a weird domain again, right? It's all real numbers, but x cannot be, what's the first thing it can't be? 0, and then pi, and then 2 pi, right? So again, we have n times pi, where n is an element of the integers. And honestly, we've done that so much, I kind of feel like you might be able to write something like that on your own. That's why we're doing it, so you can see it, you're exposed to it, it's not going to freak you out when you do have to start writing it. What's the range here? Good. Negative infinity to infinity. There's no breaks in it at all. Do you have any x-intercepts? Yes, but we want to call them zeros. Otherwise, we have to have a bunch of ordered pairs, and that'll just be weird. So we're going to call them zeros. And these have to be kind of weird, too. Where's your first 0? Pi halves. And then how far away is the next one? Pi. So it's pi halves, and then every pi after that. So this is where you get pi halves plus n times pi, where n is an element of the integers. Do we have any y-intercepts? No. Do we have any asymptotes? Yes, and it goes back to the domain, right? X equals n times pi, where n is an element of the integers. Your amplitude, just like for tangent, it's undefined. So what's the period here? Pi, just like it was for tangent. Your transformations, hang on, my board catches up. Is f of x is equal to a times the tangent of b times x minus c plus d. I put tangent, dang it. He made me laugh and I threw me off. Smart Alec. Okay. Yeah, I'm sorry. Let me just start over because I had to scribble it out anyway. So I get f of x equals a times the cotangent of b times x minus c plus d. There we go. Is that right? I should mess up again. All right, so your amplitude is undefined, but you could still have a vertical stretch or compression. Compression. So this is the absolute value of a. This is pi divided by the absolute value of b, right? Make sure you're keeping that straight again. And then this is c and this is d. Okay. Questions? Good? All right. We are definitely not doing, we're only doing a couple of things on the notes because you're not having to graph every single kind of this anyway. It's just all copied on there, so don't freak out when you see the next page. It's all fine. You just got to be able to do the basic stuff, okay? All right, so the next part is going on page 109. So if you will grab that. That's this, I think. Yes. Okay, so this is going on page 109 when we're done. Most of this up at the top we've already talked about. So we came up with these graphs, right? And I want you to, what's not in here are the asymptotes, and they're important. So I want you to sketch them in. So it says all reciprocal functions have vertical asymptotes, and reciprocal functions do not have an amplitude, but they do have a vertical stretch or compression, which is important for us. Or, I mean, they may or may not, but still, if they don't, that one is important. So then it goes on to say, it says, given f of x equals a times the cosecant of bx, and it lists them all out. So the period of cosecant and secant functions is what? 2 pi, and it's actually 2 pi divided by the absolute value of b. And for cotangent, it's pi divided by the absolute value of b. If you do what I tell you to do, these are a piece of cake, but some of you aren't even doing what I'm telling you to do on the other ones, and that's why you're struggling with them. So Instead of, so for the other ones, I was having you sketch the parent function of whatever it is that you're drawing. Personally, for me, that's not what I would do here, and I don't think that's what's best for you here either. You have to know what this is the reciprocal of. So cosecant is a reciprocal of what? Sine. So this is 1 over the sine of x. So what you should graph, and just like it's just a little tiny sketch, is the parent function of sine, just that much of it, and don't be stubborn. You need to do it, okay? For this particular function that we are graphing right now, what is the period? 2 pi, because nothing's happening here, so it's just 2 pi. Do we agree with that? Okay, so amplitude does not exist. However, there is a number here, so we have a vertical stretch of 3/2, and that's important to us. Okay, everybody with me? Here's how you do this. You know, for sine, these 3 pieces right here are zeros, right? They're not zeros for cosecant. What are they? Asymptotes. There are no shifts, so your first one is when x is 0. Then you do the last one. That's at the end of the period. What is the period? 2 pi. So we put it here at the end of the period. The third one goes halfway in between, which happens to be at pi. You with me so far? Then the next 2 things you do are these points, which were 1, right? But the reciprocal is 1, right? So you would have started halfway in between these at 1, but then there's a vertical stretch, so you go to 3/2, which is really 1.5. Does that make sense? Then halfway in between these 2, you go down 1.5, and that's really all you have to do, because now you draw that in, and then you have to repeat. Ooh, might want to draw better. Okay, does that make sense to you? It's easy. I promise it's easy, but I'm telling you, you need this to refer to, or you're going to get thrown off on what you're trying to draw. So then that means I have an asymptote every pi. So I put 1 here, put 1 here, and then it just goes up, down, like all the rest. So here I'm down at 1.5, and then I'm up at 1.5, and I sketch in the rest of it. Easy enough? No? Questions? We good? All right. Let's look at number 3. This is the secant. And what is the secant the reciprocal of? Cosine. So this is 1 over the cosine of x. So I sketch the parent function for cosine, which looks like this. Okay. What is the period for this particular function? It's 2 pi times what? 3 over 4, which is 3 pi halves, right? So it's 3 pi halves. Do you have a vertical stretch or compression? No, but you do have this negative sign. Those can be tricky. Pay attention to them, okay? So then we have, here's where we're going to start. At 0, cosine goes to 1, right? So I would be at 0, 1. There is no vertical stretch or compression, but there's a reflection, so where does this really go? Negative 1, okay? And that's an actual point. Then I go to the end of the period. The end of the period on cosine always has the exact same y value as the beginning of the period. So I go to 3 pi halves and have the same y value, which is negative 1. Then I go halfway in between. What would have been a minimum is now a maximum. So halfway in between 0 and 3 pi halves is 3 pi fourths. But I'll be up here at 1 now, right? And then where the zeros are, what happens at the zeros? Asymptotes. So halfway in between those points, which is really halfway in between a space, you get an asymptote. You get an asymptote here. And then you just repeat. Okay? So whether it's easier for you to repeat all the points first or the asymptotes or do it, you know, together, it doesn't really matter. You've got like a point and then a space and a half and an asymptote, and then a space and a half and a point. And always make sure you pay attention to the very ends, whether or not you could actually graph something out here, because you can on these. You can't just decide to stop. You got to go as far as you can. So it should look something like that. Good. Any questions at this point? Okay, then I'm going to move on to number 5. If you still have some of this to sketch in, you can always come back and finish it. Now, I'm going to throw a little kink in things because we've been drawing the parent functions for the actual reciprocal, or like for the reciprocals of what we're trying to graph. But for cotangent, I really think instead of trying to draw the parent function of tangent, which was weird to begin with anyway, if you draw the parent function for cotangent, it makes it a whole lot easier. So this is the reciprocal of tangent, but I would say on this one, the parent function of cotangent is super easy. The other ones were weird, but this is cotangent, right? That makes sense? I mean, it's a lot prettier than tangent. We're on number 5 on the back. What is the period here? Pi halves. Good. Pi halves, because it's pi for cotangent. And then I have a vertical stretch of what? 3. Okay. So there are no translations. So for cotangent, because this is the actual cotangent graph, I have an asymptote at 0. So I'm still going to have an asymptote at 0. Then I put the next one at the end of the period, which is at pi halves. Right here. Halfway in between there, I have a 0. And then you have to be careful that you're doing it in the correct direction. Halfway in between these two, you go up to 3. And halfway in between these two, you go down to 3. And then you repeat. We good? I know, you feel like your little hand's gonna fall off. It'll be fine, I promise. Okay, so while y'all finish that up, I'm going to hand out the assignment, but you're not doing all of them, so wait. Once I hand them all out, then I will tell you which ones you are doing. You're not even doing all of the ones that you can do, because it's just not necessary. Are there any questions at this point? I know most of y'all are just trying to finish your graph, but do you have any questions? Okay. Even if you're still trying to finish this, grab the assignment so I can tell you which ones you're doing so you can circle it, and then I'll give you time to finish. You're only doing on the front numbers 1, 3, and 3. 1, 3, and 3. Okay? Both of them. The other ones you can cross out. We're not doing it all. Yeah, so just 1, 3, and 3 is all you have to do. You only have a few minutes left in here. You could probably finish it before you leave. You could at least get them started and ask me questions if you're confused. Okay. On the back, you're not doing. None. Huh, you got one. You're only doing 1, 3, and 3. Literally 3 graphs. That's it. It's right there, isn't it? Oh, no. Sorry. I can't count.